and it can see the entire proton also. So for smooth charge distribution inside the target, that means when q square tends to infinity or lambda tends to 0, if there is smooth charge distribution, then we have W1 tending to 0, W2 tending to 0. However, what if, remember in the last class I talked about the Rutherford scattering. If there was a smooth charge distribution, then we will never get the small scattering at small angles. The few numbers also. So, if the charge distribution is concentrated in very few space points inside the proton, then it was postulated by Jorken in 1967 that this W1 and W2 at very high q square and nu, they will have this sort of scaling. They will behave like this. Now, you notice two very important things. One, the form, there is a proton mass, there is over nu over here. Another, this F1 and F2 are dimensionless numbers. And do you see anywhere this q square? No q square. So, he just postulated that if the charge is concentrated inside the proton at very few points, then there will be no q square dependent. So, q square independent phenomenon. And what is this small w? This is just the inverse of the Jorken variable. Just this. Now, let us look into the experiments over here. So, this is all theory, and now let's look at the experiment. So, Stanford Linear Accelerator Center, they did experiments, quite old experiments, and there electron of 5 from 5 to 20 GeV, it was bombarded on liquid hydrogen target. And I am not showing you the observed data. Maybe in the online class I will show you the plot. And from the observed data, interestingly, we have two very important observations. I would like to focus on those observations. Now, the first observation is Jorken scaling, which is, you see, we observe this sort of behavior from just like what has been predicted by Jorken. So, F1, which was initially function of x and q square, it is just a function of x. Similarly, F2 is also a function of x. So, this means there is no q square. So, this q square independent behavior, this was already predicted before by Jorken, right? So, this means that we can infer from this q square independent behavior that the scattering is happening from point-like constituents inside proton. So, the scattering, anti-inelastic, deep inelastic scattering, where large momenta is being transferred by the electron to the proton, is being happening due to from point-like constituents inside the proton. And that's the reason. Remember the diagram which I drew in the very first part of my lecture, there were very small tentacles going on. So they represent the point-like scatterings. Now, this is the first observation. What about the second observation? The second observation is, you see over here, the second observation is that they are not unrelated. This F1 and F2 are not unrelated. In fact, they are related. Now, so the first observation tells us that there are very few point-like constituents inside the proton. Understand the significance. The first observation, q square independence. From there, we observe this Jorken scaling, and this tells us that the charge distribution inside the proton is not uniform. It's rather very ununiform. Charge is distributed in very few points. Okay? And the scattering of the electron at very high energies is happening with those very few point-like constituents inside the proton. This is what the first observation is telling me. The second observation is the one where I can relate F1 and F2. So the second observation is that F1 and F2 are not unrelated but rather related for q square greater than few GeV square. Right? And you see the relation, what sort of relation will be there between F1 and F2. In fact, it can be shown, you can see in the high energy physics textbook, that suppose you assume that these point particles have some spin, okay, you assume, then depending on the assumption of their spin, the relation will be decided. And we experimentally observe this relation. F2 is equal to twice x into F1. And this relation is known as Callan-Ross relation. Okay, and you see the inference of this particular relation, this nature, this tells us that the inelastic electron-proton scattering is basically elastic scattering of electron from the point-like constituents that we know, but those point-like constituents have spin half. You understand the significance of this relation? The significance is that it tells us about the spin of the point-like constituent. This is important. So in the exam I can ask you. Normally you are just asked to derive, but sometimes it is also important to understand the significance of the very simple results that we have. So this sort of relation, in fact I will show you in your online tutorial class, I will show you that if I assume a different spin, the relation will change. Okay? Any questions?